Alright guys, here's an overview of exercise 18 from Lab 7. This is troubleshooting parallel circuits. And in exercise 18 we have two resistors and a lamp to represent different power dissipations. They are all hooked in parallel with one another. On my bus line here, you can see I've tied together the positive and negative power distribution bus rails on either side of my proto board. I'm actually going to be putting my power supply in up top here with my negative on this side and my positive on this side. I'll later on use this as a takeoff point for measuring current for each of my branch currents when I need to check that. And you see my resistors from the negative, they bridge across, and each of these are branches coming to the positive, negative, bridge to a positive, and over. And in the case of my lamp goes from the negative here through the lamp itself and back to the positive on this side. And then, as I said, these rails are tied together. We're going to be measuring current with an ammeter over here. So this one is set to measure current, and I'm on the 200 milliamp scale. We're going to start off measuring resistance with this meter here, and then I'll change that meter so we can measure our voltage. And right now this is our circuit schematic. We're going to put 10 volts DC into this, and then we'll record our measurements over here on the side. So let's get started with this. I'm going to set this up, and then we'll do some measurements. Okay, so the first step is to measure total circuit resistance. And you see we're right about 15.4 ohms in that range. So we have the ohm meter connected in to where I ordinarily would put my power, and it's recording the total circuit resistance for everything that we have hooked in here. Remember, in parallel circuits, our total circuit resistance is always going to be less than our smallest resistor. Okay, and in this case, the smallest load is the light bulb itself. The light bulb is probably carrying about 17 ohms of resistance or so in it. And now remember, that is in a state where the light bulb is off. The lamp does have thermal resistance associated with it, and we're going to see a change as we compare some calculated measurements within this lab. We are going to see a discrepancy from some of our operational measurements to what we're getting here before we apply power on this circuit. The next step is to convert this over to apply voltage. So I'm going to change my ohm meter over there to a voltmeter, and I'm going to hook power into this circuit. I'm going to do that. While I do that, I'm also going to connect my ammeter to that. So my ammeter is hooked to my power supply. Took the negative probe and hook it into the negative wire coming from my power supply. My positive probe comes out and actually links to an alligator here that I'm going to take this alligator and hook it into the negative bus rail on the circuit here. So give me a moment, I'll set that up, and then we'll see what kind of measurements we get. Okay, so here we all set up. We're going to turn our power supply on. So take a power here and set my current knob just to the midway, and I've already preset this to the 10 ohms using my analog gauge. Analog gauge says 10 volts, and looks like we're at about 100 milliamps or so on our analog gauge. We can't get a very specific reading. Let's come down here. What does our ammeter say here? Our ammeter says 115.3 milliamps. Okay, as we come back, notice our lamp is on, and our resistors aren't doing a whole lot of anything. And you see we have 10 volts on our voltmeter. So these are overall measurements. Let's go ahead and transfer those onto our paper here. We had a total resistance of 15.4 ohms. We have a total current of 115.4 milliamps. And we have a total voltage of 10.03 volts. Okay, using Ohm's law, we can do some calculations to see how these operational measurements correlate out. Let's take the 10 volts, 10.03 volts, and divide that by our current, which is 115.4 milliamps. Okay, and then you're going to get an answer that is in k ohms because we're dividing by milliamps. So our answer will be in k ohms. Stick that into a calculator, see what you think, and does it make any sense when you compare your measurement here to what we get up here. Now keep in mind 15.4 ohms is 0.0154 k ohms. So see how that calculated measurement compares as we assess the basic parameters of this circuit. Okay, so that calculated out to be 0.0869 k ohms or 86.9 ohms, which is significantly different from what we measured. But remember, when the lamp is on, there's a thermal resistance to that is higher than when it's off. And we'll see that later on as we take each individual component measurement. So our next step here is to introduce a problem. They ask you to open up this circuit by raising resistor number 2 here. And you see what I did? I moved it out of its position, so it's effectively taken out of the circuit. We know where the problem is, but we're going to learn here just how difficult it is to find an open component in a parallel circuit. Now, one of our first indicators that there's a key problem is our 115.4 milliamps has gone away, and our ammeter is now reading 97.8 milliamps. We're still at 10 volts, 10.0506. Okay, so my voltage really hasn't changed significantly. My light is the same brilliance, and otherwise the circuit looks pretty much the same. The exception is we did raise this lead. You'd have to examine it really carefully to know that it's not in the circuit. Doing some Ohm's law calculations, we can see that okay, our total current isn't what we thought it would be. So now, how are we going to go and find this problem? What kind of measurements are we going to take? So what we're going to look at is we're going to compare voltage, and we're going to compare current measurements for each of these. And what we're going to assess is how has current changed through each of the branches. How did current change on this one? Is there a current change on this one? And is there a current change on this one? So we're going to set our circuit up to take those measurement readings. And very simple task to do here. I'm going to leave my meter as you see it here connected, but I'm just going to move the location of connection so that we're assessing the branches. So give me a moment to set that up. Okay, so as we started this out, I did switch my leads on my ammeter now so that my negative probe comes to this negative point on my bus line. Basically, I'm going to lift each of the lines that goes to the negative bus line for each branch. So I lifted the lamps here, and then I'm going to insert my positive lead of my ammeter there. That completes the circuit, and the light goes on. So my lamp, with the fault in there, is pulling 66.3 milliamps. Okay, so I'm going to come back down here. I'll reconnect my lamp. We know that this is a circuit with the break in it. I'm going to lift its negative side. Sorry, got off there. And connect it. And oh, we got 0 milliamps. Well, that makes sense because there is an open break right there. But resistor 2 saw 0 milliamps. I stick that back in place. And the last one, resistor 1 here, I'm going to lift its negative leg out and put my positive lead on there. I do need to break the circuit in order to get an effective, oops, let's try this one more time. Sorry there, guys. So here we are. We're connected to the broken lead, and my meter is saying 31.4 milliamps. So I'm seeing on my 3 branches, I see approximately 60 some milliamps here, 62 I think it was. I saw 0 here, and when I broke this and lifted it out, I saw about 31 milliamps as I looked through. So I reconnect that in the circle. That's checking the current across each of these. Now, what do you think we'd see if we were checking voltage? So in checking voltage, what we can do is take our voltmeter over here, which currently is set to look at the total circuit voltage, and we can come down and look on either side of the component. So give me a pause as I set that up for you. Okay, so what I've done is I have removed the ammeter from the circuit. So it's taken out altogether, and I have the voltmeter over here looking at the circuit. My power supply is connected up at the top. Now my voltmeter negative probe is right here. I've got it right on the negative bus. Currently I put a wire in, just a probe wire on the positive side of the light bulb to measure the voltage there. As anticipated, I am pretty much seeing source voltage. There's a slight change, but we're at 10.17 source voltage. That change most likely is affected because we took the ammeter out of the circuit. Now, if I move my probe down to the faulty resistor, remember this is the one with the open on it, and I'm asked to look solely at the resistor itself. So to clip into the resistor itself and to see, do I see anything? And my meter says 0. Well, that does make sense, because remember, this thing has an open in it. Come over here to my good resistor number 1, and we'll hook that on there. And let's see what we got. Again, we see the source voltage. So the faulty component here did not have a reading. What about if I bridge the gap? If I go to the other side of where the divide is, notice when I bridge the gap, I do see the source voltage. Okay, and just to do it properly by the lab examples here, we're going to take this negative lead, and they say put that on that side of resistor 2, and then this on this side, and again you see the same result. You see the source voltage. That's true when you're using a voltmeter. You can find an open flaw using a voltmeter as long as you're bridging that open flaw. Now, it's very hard with a parallel circuit to find opens like that. However, we were able to identify where our problem was when we had a 0 milliamps reading on resistor 2. And we also, if we probed in the right spot, we're able to see that there was a 0 volt reading across the load there. So we're able to isolate our problem. It just takes some extra steps to do that. We were also able to identify that the total resistance in this circuit you're going to see is significantly different. So one final setup, and I'll set that up to measure total resistance with this flaw. Okay, using an ohm meter to find the flaw. Well, this is the total circuit resistance. The flaw on resistor 2 still exists, the open. And I now have 17.6 ohms. If you remember back in the beginning, our total circuit resistance was 15.4 ohms. So when we come down here and look at the circuit, you examine real carefully, you see that the flaw still exists there at resistor 2. And what I'm doing is looking at total circuit resistance. Your next steps are to go through and examine each component and its resistance. So I'm going to move my positive probe of my ohm meter down here to the lamp. So I'm looking just at the lamp. It still says 17.3 ohms. So it really did not change. Now, if I look at the open component, okay, I don't know it's open, but there I am at the open component. Go up there, oh, I've got an infinite reading or a reading of 1. So that is an aha. If I get the right place on that component, I might be able to identify that was where my break was. May not be able to identify a specific problem. When I look here at resistor 1, I'm back to my 17.3. So my total circuit resistance did change because there was an open in it. Now I only have 2 loads that are accounting for it. If I get on the correct side of the break, we have an infinite reading. But if I'm on the opposite side of the break here, I'm going to end up seeing that 17.4, 17.3 total circuit resistance. So depending which side of the break you're on, an ohm meter can also help you identify or get close to the source problem. Your final step here is to reconstruct this circuit, and you're going to set it up for a short circuit analysis. In order to do this, we are going to hook a protection resistor in series. Basically what you're going to do is disconnect your source power and bring one end, your negative end, into the resistor lead, and then have that resistor lead come into your board here. I'll have that set up for you in the next video section. Okay, the final step to our lab is to look at a short circuit in parallel and try to troubleshoot that and find that. So we've modified our setup according to the instructions. We did add a 120 ohm resistor, and what I did, or what I like to do, is I put that on the end of the bus line, and I've hooked my negative supply line into that resistor, so it is in series, and basically that's simulating the internal resistance of the power supply. For our purpose, it's a protection resistor. It does change the circuit characteristic a little bit when we're looking at things overall, but it's a protection to keep things from burning up here when we short this out. We also modified our power supply to be 7 volts. So we're bringing 7 volts into the circuit. Again, the rest of the circuit setup is very similar. Now I've taken this yellow alligator over here and I've hooked it to resistor 1. This is what's going to be creating my short. Before we do that, I want you to look really carefully there at the light. You'll see it's a very dim glow. And I could turn the voltage up a little bit and get a little more of a glow to that, but I just need an indicator that current is flowing there in the circuit. Now, you know from previous labs that when you create a short in parallel, everything goes out. So here we go. We're going to short this guy off. And notice my dim glow has gone away. Okay. If I measured volts with a voltmeter here, what do you think I'm going to see? Let's go ahead and check. We're going to check voltage. So I'm going to take this guy, turn him back to volts, and we'll put our negative probe there and our positive probe here. So looking at resistor 2, looking at my volts, I have 0 volts. I'm going to see something similar for all of these. And why do you think that is? Why do you think that we have 0 volts with our short in place here? So it doesn't matter where I go on here, I'm going to read 0 volts. The next check you're going to end up doing is the resistant check. And so we're going to turn our power supply off, and I'm going to remove my power probes, and then we're going to check for total resistance here. So I'll pull this out. We're not going to factor in our internal resistor up there, and we're going to look using an ohm meter. What do we see with the resistance check here in terms of total circuit resistance? So on my positive side, I'll hook that in, and on my negative side, I'll hook that one in. Okay, and when I look over here, I have 4-ish ohms, 4 or 5 ohms. Now remember, initially in our circuit setup, we were at 15.4 ohms, and you know, here with our short in place, we are seeing a pretty low resistance Well, now I guess it's down to 2 ohms as it settles out. We were really low resistance. The wire does have some resistance in it. This could be as low as 0 ohms, but these alligators actually do have some resistance. Remember, in parallel, total resistance is less than the smallest resistor in there. So we're accounting for some of the resistance in wires here to get such a low reading. Actually, it's still settling out, still dropping over there. I'm down to 1.8, 1.7 ohms as things kind of settle out. So my resistance is extremely low with that short. Unfortunately, isolating a short in a parallel circuit is an extremely difficult task. If we go through and remove each of these components, well, let's see what happens to our resistors. So I'm going to remove the light bulb, and as I pull the light bulb out, I'm still at that low 1.5. I'm going to remove resistor 2 and pull it out, and well, it's jumping around and settling out again, but I'm still at a pretty low value. My short is, because there was no change, my short is kind of an obvious piece there. Now, if I went back through and I removed the shorted resistor, what I would see is my resistance would jump up. So isolating a short using an ohm meter is a difficult task, but it can be done in troubleshooting parallel circuits. Use this information, answer your questions, complete your lab report, and ask if you have any questions.